on our third lecture on antimatter models of mechanobiology.
Okay. Hi, so good morning, everyone. I thought there might be some people wandering in a little bit late, so I thought I'd just start with something, just a couple of slides to give you some ideas about where we might find topological defects, which are actually useful in biological systems. Because we're going to be talking quite a lot about topological defects later on. Isn't it working? It's on.
Turn it on.
Can you turn it up?
Yeah.
Yeah, is that okay?
Yeah, we hear you.
Yeah. Okay, so two cute examples just to get people started. So what this is Mycoxanthus, which is a sort of bacterium which crawls around, and it sits on the substrate and crawls around. And then it wants to form fruiting bodies, and so it wants to form a lot of layers, one on top of the other. And the way it does it is that the second layer and the third layer, each successive layer forms at a position of a +1/2 topological defect, and then the layers go away and you get holes, these holes where there are no bacteria at the positions of the -1/2 topological defects. The reason is that defects correspond to stress in places where there are large flows, so it's easier for the bacteria to escape at those points and to move up to the next layer or to create a hole in the original layer. The second example is topological defects in the mesothelium. The mesothelium is essentially a layer of cells which cover organs, and for cancer to spread, the cancer cells have to burrow through this mesothelium. And in this paper, what they showed is that it's much harder for the cells to be cleared away and pushed away in the region of the topological defects, that they tend to burrow through at the points where they see the topological defects. And the reason for this is that around the defects, there are more cell flows, and so it's much harder for things to be pushed away, so they tend to penetrate instead. So there's this link. I mean, we're a long way away from reality, but there is this link suggested between topological defects and things which are actually going on in biological systems. And almost certainly the link is just the ordering is wrong at topological defects, and so there's more stress and strain at those points. We'll see some more examples as we go through. Okay. So what I've done up to now is introduce active turbulence to you, and then look at things which are a bit different about different sorts of active turbulence, these slightly less well-known instabilities, what happens in confinement, and the idea of active anchoring. And we started looking at mechanobiology. We looked at active anchoring and then said that this might be responsible for cell sorting in real biological systems. Today, we're going to carry on with this idea of mechanobiology. And we are going to first ask the question, how do confluent cell layers move? Then I'm going to do a researchy type thing, which is asking whether confluent cell layers are extensile or contractile. We were worried about this for ages because cells are contractile, right? If you're a biologist, cells are contractile. But if you look at topological defects in cell layers, turns out that they move towards their head, which means that they're extensile. So what's going on? How can we explain that? And what I want to show you is that it's not right, actually, for cells to think of them as contractile or extensile. They can be both. They can switch from one to the other. I'm then going to talk about another sort of model, because we've talked a lot about continuum models, and up to now, up to this bit, it's pretty much continuum. We've heard a lot about vertex models. Another sort of model is phase field models. It's a sort of alternative to vertex models. So it's nice for you to see, I think, about these sorts of model systems. And I'm going to ask, how do they behave when you put different sorts of forces in them? And then we'll jump back to vertex models. I'll tell you why I'm jumping around a bit, okay? And show some recent work where we're trying to push these vertex models to be more like the continuum models and to be more like biology. Now, I wrote that word to remind me to say to you, scale. It's important to realize the scale on which we're actually doing these, on which we're doing these models. We've looked at continuum models, right? And some of you are worried about continuum models because they don't put in details. They put in symmetries. They look on a coarse grain length scale. They make systems which are different on a small length scale look the same. And so they can answer some questions, but not other questions. Models like the vertex model has been very helpful in helping us think about the shape of cells, and I hope to convince you perhaps about the dynamics of cells as well. Vertex models are one step down. You still don't resolve what's going on inside one of these cells. You just look at the shape of the cells. And these phase field models are a bit the same. And then we've heard from Ulrich and other people last week, the Knoll paper, which was mentioned, where people are now trying to go one step lower and say, okay, we're trying to understand the forces on these cells, but where do the forces come from? Linking the actin now into what's going on. And of course, there are many people looking at very much more microscopic models where you actually look at the details of what's going on in the cell. And they're all useful, but they're all not perfect, and you need all of them to try and understand what's going on. And in the end, experiments are going to be the right thing, which actually tells you what actually happens. So let me just talk about how individual cells move, really just to set the scale on which I'm actually going to think about these models. Okay? We know about these cells, we know about how they move, we've heard a lot about that. But if you want a minimal model of what's going on, these things have some sort of polar driving, which will move them in a certain direction by a fluctuating polar force, because we know that they do a self-avoiding walk, and then some sort of self-contractile activity, which takes my elongated cell, which has been pulled out by the polar force, and pushes it back, so it's a more sensible shape. So a minimal model of a cell would be polar driving with a fluctuating polar force, and then some sort of self-contractile activity, which gets it back to the right shape. This would biologically be due to the focal adhesions with the surface. This would biologically be mostly due to the actomyosin network pulling itself in. And, you know, that's fine. I think there wouldn't be many complaints about that. How do you write down a similar model if you've got a cell layer? And let's think, to start with, about just an experimental system of a cell monolayer on a surface. How does that move, and how I write down a minimal model to understand how it moves? That's the thing we're trying to do. So let me start by actually talking about how this thing moves. All right, we're thinking of epithelial cells, the ones that line the cavities of the body. We've heard lots about epithelial cells. They really like sticking to each other. They really like forming layers. And we're going to think about confluent cell layers. And the confluent cell layers move in various ways. We've seen this before. This is one of the ways that they move. So let me start by trying to summarize how these cells move. Well, first of all, we've got jamming. We've heard a lot about jamming, okay? As a function of the shape of the cells or the density of the cells, they jam. They still move locally, but they don't move relative to each other. Also, as we heard yesterday, they can flock. This is the cells on the inside of the egg chamber of Drosophila. And for some reason, they move round and round coherently with each other. So here they are moving round and round, and you'll see a blob which enables you to follow them in a minute. There they are going round. Okay, so there are definitely cases where cells flock, and we saw lots of those in the lecture yesterday. When you have the edge of something, the cells move outwards, and they move outwards in a coherent way. These things also sometimes show active turbulence. Okay, so why do I think this sort of jiggling around? Why am I calling it active turbulence? Just sort of cells randomly jiggling around. Okay, so I'm going to go through some of the evidence now why I think this stuff is like active turbulence. Well, first of all, if you look at the velocity fields, you get these localized patches of high velocity, and you get vorticity. One of these is from a simulation showing a velocity field, and one of them is from an experiment on cells like that. And you can see that they look pretty much the same. And if you do the statistics, it comes out pretty much the same. Topological defects all over the place. People have now looked at lots of different cells, both long, thin cells, and also the squishy cells. And you get all sorts of topological defects, which behave like active topological defects, which appear and which disappear. Then I think one of the really lovely experiments is one from the Paris group. They took cells and they put them on a long, thin channel. So it's like a confined system. And what we learned yesterday is that if you have confined cells, what happens is that they will move along the channel due to the activity, and they'll move due to a shear flow. And that's exactly what these things do. This is a velocity field. They move in a regular unidirectional shear flow. And if you try and match it to the paper, to the original paper by Boituriez and Gianni, then what you find is it matches exactly, essentially exactly. So this thing really is behaving like an active pneumatic. We saw this yesterday as well. If you confine them in a square, they're going to start going round and round. So that works. These are the original experiments which showed topological defect and pneumatic order in this MDCK layer. So how do you sort of match these cells, map these cells onto pneumatic order? All right, so these are the cells. You put a director along the long direction of the cell. We're all used to that. People were much less used to it when we did this. And you plot what's happening here. So these are the directors of the cells, the direction the cell is going. And you can identify topological defects. And the topological defects move towards their heads. Whoops, panic, right? Things moving towards their heads are extensile. Cells are meant to be contractile. So what on earth is going on? We'll come to that. The other thing we did in this paper, and when I say we, I mean Thuan Beng So in Benoit Ladou's group did all the experiments. This is the number of defects as a function of time. Number of topological defects as a function of time. And what happened here is that the experimentalists added blebistatin to the cells. And blebistatin is a sort of sleeping pill for cells. So if you add blebistatin, what happens is that these cells go to sleep, and so they're not active anymore. So they're not active, so the defects move towards each other and join each other in pairs and annihilate, and the number of defects goes down. And then if you wash out the blebistatin, the cells wake up again, and what happens is the number of defects goes up again. It becomes active again. So I think this really is quite nice experimental evidence that these things are active. Our biology colleagues were worried about why the system should do this. Yeah, sorry. Just the long axis, essentially. I mean, it's a bit more than that. We actually averaged over sort of 3 by 3.
If you look at the one on the top right.
Okay, well, I mean, we actually took a 3x3 pattern averaged, and this data is probably from a long time ago, but yes.
It's concerning because oftentimes when you have a field, there's weight averages from the field, so you can get things that are pure pneumatic. I know this from my own experience where there's no pneumatic order. I've just with all these so because it's looking for fields. So I think I have similar concerns with Sheila as I've described.
But from what we said yesterday, you are allowed to have pneumatic things even when the cells are circular. Okay, so I'm not worried about that. I might be worried about the data analysis, but you wouldn't get patterns like this, I think, if the data analysis was screwing up. I mean, you'd best to be able to identify defects. Yeah, and the fact of the defects, and also it's now been seen a lot in different systems.
I think it's
Demoralized cells.
and other types of cells.
Well, in MDCK as well. I mean, doing experiments on these types of cells now. We'll see some more later. All right. But I'm going to, Margaret says that these things are not pneumatic in her experiments. And that's fine. And we'll see in a minute maybe why. All right, so the jury is still out whether or not these squishy cells can actually be pneumatics. And we have to be careful. We have to be careful because it is local pneumatic order. This is not long-range pneumatic order. And if you really want to get confused, people are worrying about whether they've got hexatic order, hexagonal symmetry, but I don't want to go into that. Anyway, so our experimentalist colleagues were very worried about having some sort of biological reason about what happened near these topological defects. And what we actually found is that the cells tended to die, undergo apoptosis near the defects, and that they interpreted in terms of extra stress on the cells near the defects. Extra stress meant that YAP moved around in the cells, and the cells tended to preferentially undergo apoptosis near the defects. Now, just because of where I come from, I've tended to concentrate on active turbulence and this pneumatic motion. A lot of cells move in a polar way, and I tend not to talk about them because we haven't really thought about them, but this is a bit unbalanced, all right? I think you've heard from loads of other people about polar motion of cells, so let's make that clear. So now what I'm going to do is I'm going to go through 3 experiments which I really, really like, which if we are going to understand what these cells, we have to understand these experiments. So this is a really lovely experiment, quite an old one now, from the Milan group. And what they did was look at MDCK cells, again, sorry, MCF10A cells, but squishy cells the same way. And this is a picture of the velocity field, and these things are undergoing active turbulence-like state. They then add RAB5A, and the experimentalists tell me that what RAB5A does is muck up the cell-cell junctions in some way. Sorry, others might be able to do better with that, but they couldn't. They don't really know what it does, but they think it does cell-cell junctions. And what happens is that you cross over from this active turbulence to this state where everything flocks. Much larger velocities in a particularly well-defined direction. So this is a picture of the velocity of these things. This is the velocity where you don't add the RAB5A. They're just sort of mean velocity, so they're moving around randomly and rather slowly. This is the velocity where you do add the RAB5A, and you can see that the velocity goes zooming up. And, for a biological experiment, that's wonderful. You can actually see that there's a difference in the data, right? So it goes up and down again. So somehow mucking up cell-cell junctions makes these things suddenly decide to flock. Okay, so this shows active turbulence, flocking, active turbulence, flocking. I'll play that again because it happens quite quickly. Okay. Any questions? Yep.
When it goes, we're at 5A was taken out, or does it just naturally
It naturally seems to decay away and stop.
back to
Yeah, goes back to active turbulence. Yeah. Yep.
Gravitational order, or just like the correlation, like the velocity correlations is a bit bigger?
I mean that the velocity arrows look like the ones there, yeah, which means that there's correlated motion. Cells tend to move in the same direction, all right? So it's a velocity flocking thing. I've no idea whether there's any pneumatic order here, all right?
Control case also has just a shorter correlation like that, right? Like nearby cells. Or is there just no?
Yeah, the velocity correlation length would be shorter in this case, right? But the velocities are much, much larger over here. Yeah. Okay. All right, so this is an absolutely ancient experiment. And this is this thing called contact inhibition of locomotion. This is a sort of fairy tale in biology. It's a belief, right? As far as I can see, there are no modern experiments which really show what's going on here. Somebody might like to correct me because there's lots of biological experiments. The original experiments were very beautiful experiments by Abercrombie a very long time ago. He had two cells and they approach each other. This is actually the front of the cell, remember? They approach each other and they tend to move away from each other. So pairs of cells come together and then tend to move away from each other. So then people sort of extrapolated this idea to colonies of cells. And what they say is that colonies of cells don't move in any direction. They do if they have a free edge, but if they haven't got a free edge, they don't set off moving in any direction. And within a colony, the cells don't seem to move very far. And this is because they're much less likely to form lamellipodia. And so as you put them together, the strength of any polarization forces decreases. That sort of looks like it happens. If you look for lamellipodia in one of these layers, you can still see them, but they seem to be less big than they would if you had single cells. And biologically, it sort of makes sense, right? That if you're a cell in a layer and you're trying to pull like mad in all different directions, you know, it's just a waste of energy, really, because you're not going to go anywhere. So polar forces tend to be turned off, brackets probably, in cell layers. But as far as I can see, there's a big jump between here and here, which has never really been checked in experiments. Very happy to be told I'm wrong from biology people, but this contact inhibition of locomotion for cell layers seems to be more a belief than anything else. Then the last one is a very recent experiment. And I looked at it and I thought, wow, that's beautiful. All right. What this was in the Princeton group was that they took a substrate. I mean, it's really just a simple experiment. It's so clever. They took a substrate, and on one side of the substrate, they put something which looks like an extracellular matrix. So the cells thought they were sitting on top of an extracellular matrix. And on the other side of the substrate, they put E-cadherin. And E-cadherin is the thing which forms the bonds between cells. So these things thought they were attached to other cells. And then they just watched them. And the ones on the extracellular matrix type substrate had a velocity like this. Random, but this is the average velocity. They weren't going anywhere. They were moving around at random. And the ones on the ECAD substrate had a really tiny velocity like that. And then the different colors are just what happens as a function of time. This thing slowed down as a function of time, presumably because of cell divisions, making it harder for things to move. All right, so that shows, Margaret, that shows, right? Sorry, I should have said before I started explaining that it really depends on the substrate how these things move. All right, so it's really a simple experiment that makes absolutely clear that the substrate is important. So why, it's not obvious what's going on. Someone I was talking to yesterday had a really sensible idea, which, if you've got ECAD there, the things just stick down to the ECAD and they can't go anywhere. But then there's ECADering between cells and they can move relative to each other. So anybody got any ideas they would like to explain what's going on there, or questions? Sorry? You mean they'd spread out more? They'd be bigger on the substrate? These are the pictures of them. They're a little bit bigger on this side, but not much. Mm. Not really, because these things are three-dimensional. Yeah, I think, right? I always tend to think them as 2D and then get all upset when I think them in 3D, but they do have sides where they cling to each other. But maybe, I mean, it obviously makes a difference if they're towards each other or to the substrate. Yeah. All right. Yep.
Some paper was also written that they form stress fibers
Mm-hmm.
with the ACM side, but not as much in the other side.
Yeah.
And this could be very much related to the way them stress propagates along the cell, needing those stress fibers.
Yeah. Yes, that's right. That's right. That's saying the same thing one level down with the biology. Okay. Just saying these things form stress fibers and those don't. That makes a lot of sense because these actually move. But then why do they form stress fibers? Yeah. Yes. But then, the ECADs are the bonds which they form between themselves as well. So they don't seem to be so stuck together, but maybe there's some extra biology going on there. All right. Okay, so, I mean, I think what I'm showing you is that we don't know what's going on. So now, because it's late in the week, we're going to have some show and tell. And then Andy Rudd is very kindly going to come and talk about this, because this really, yeah, this really makes it clear, that even I had a list of different ways cells move, and he immediately comes and tells me a different way cells move. So this is really a cute experiment.
All this time, like the topological request form by like in the cell photograph by itself. Here we are trying to impose the topological request by patterning the substrate. So on the left, there is fibronectin, which is a naturally grown the cell substrate is coated with fibronectin, which is a naturally occurring ECM protein. So cells like to move in that. And if you see the video of that, you can see that the cells align along the ridges. They don't care so much about the other cells and they are sliding past each other. Quite nice. If you now change just the substrate and put it to poly-D-lysine, which is not a naturally occurring substrate, the cells don't like it so much and they have a completely different motion. Okay? Same cell, same substrate, same type of growing experiment, just completely different collective motion from the same experiment.
You should explain what they're doing there, because it is a bit hard to see from the video. Yeah.
So, compared to the first video, I was playing. So you can see that in here, the cells actually completely ignore the cues that are there from the substrate, and we just care about the other cells and start forming cell. The cell adhesion becomes stronger compared to cell substrate adhesion. As compared to the previous cases in which they really didn't care about the other cell, they were just moving around the cell, like they were just moving with the cell substrate. Yeah.
So which one is the portion?
The whole thing.
So the circle?
Yeah, the whole circle.
none of what's on the surface is reducing.
No, this is a part of, like, you can think of it like an inch, small,
Oh, they're richer.
yeah. Like 1.5 microns in height.
So polylysine,
Polylysine on the right, yeah.
that doesn't engage overheat, doesn't it's like thick membrane.
Yes, yeah,
So often that's used to immobilize.
yeah, but they use to remember about.
Reading their own.
Yeah.
Have five.
They have hybridization, but not in the same concentration as this. And that kind of explains why these two different.
Okay, so I'm you got a second mode of motion. So this one here, correlate.
Yeah.
And the right one is moving towards the center.
They're sticking to each other. So you can see that the cell actually starts sticking to each other and these start pulling towards where there is a higher density of cells. And at the end, they start moving towards the center because there's higher density of cells already.
This reminds me of something like the de-wetting work. Once you alter the activity of the surface, it just might all collapse.
I don't know.
Great. Thank you very much. Good. Anybody else got any fancy ways cells move they want to tell us about? As a sort of show and tell? No, right. Okay, so I mean, I think these ideas about how things move on substrates go some way to explaining Margaret's problem, or my problem, as the case may be, about why sometimes MDCK looks like they're doing active turbulence, and sometimes they look like they are not doing active turbulence. Certainly, if you look at suspended MDCK without a substrate, it just sits there. It doesn't do active turbulence. Soft substrates, it probably doesn't. Harder substrates, I think that's when you see what's going on.
Actually, I understand. I guess I have concerns about the analysis of the kinetic field, even in the case of the substrate.
Okay.
We still have it. I just want to.
Yeah.
I understand that. Yeah, it does affect it.
Yes, yes.
But I also, even in the case of the substrate,
Yeah.
I have significant concerns about interpreting a kinetic field.
Okay.
There are cases like this where you get induced alignment and polarization, but I think NCK cells are pretty loyal, and it's been I don't know, some of the data, the experimental analysis of it as kinetic field questionable to me. I don't know. That's my opinion.
Okay, well, you'll hate the next bit then. Yeah. Right. So we don't know what's going on. Right. I think this is fair enough. I don't anyway know what's going on. What sort of questions do we want to ask? If we're going to do modeling, what sort of questions, generic questions about these cells? Would someone like to tell me some interesting questions? You know, if you had a student, yeah, go ahead. How do they communicate with each other? That's a nice one, yeah. Others? Yep. Oh, we've got an engineer here, biologist and engineer. That's right. Can you actually do something about it? Because it would help to understand it to do something about it. Anything else? Okay, those are two things which were not on my list. All right. So this is the sort of questions that I've been trying to ask. Okay. So first of all, it would be nice to actually understand what the forces are like, right? When are we looking at polar forces, and when are we looking at pneumatic forces? Or indeed, there was some very nice work by Cristina Marchetti, where they thought about fluctuating polar forces. Because if you have a polar force which fluctuates quickly on the time scale you're looking at, that would be the same as a pneumatic force. Of course, we have to worry about the underlying biology. In the end, that's the most important thing. How much difference does the substrate make? We saw that if you have free boundaries, these cells just take off. Are cells behaving in a different way on free boundaries and not free boundaries? We sort of answered this, okay? Why can circular cells still give me active turbulence? These things can, there's an instability by which they can form a pneumatic phase. And then, are these cells extensile or contractile? And it's this one I'm going to talk about now, all right? So this is a piece of work which is actually research type work, and the experiments are due to Jacob Nottbaum and his group, and the theory is due to Marana Liam and Guan Ming in my group. So, MDCK again. This is an MDCK island. And the experiments are that two things were measured. The direction of the cell, which is just the long axis of the cell, and the direction of principal contractile stress on the cell, i.e. the zeta cube term. So the direction in which forces were pulling inwards on the cell. We're assuming these things can be described by this stress field zeta q, and we're looking at the direction in which things are pulling inwards. You heard from Kirsty, and we've been going on about it a lot, okay, that if the cell is like this, so its shape axis is long here, right? This is its long axis, and its stress axis is like that. It's a contractile cell, and the stress and the shape are parallel to each other. Fine, we understand that. Okay, same could happen for one of these MDCK cells. It's elongated in this direction, and so its shape axis is along here, and its direction of principal contractile stress is in this direction. I'm assuming it's pneumatic, so I have dipolar forces. Okay? But that's fine, but then what happens if that cell actually does get squished by the forces? It gets squished by the forces, and it ends up like this. Right? Squishy cell, so you can squish it. And what happens is that this is the stress axis, pulling it inwards, but the shape axis is now in this direction, okay? And so it's looking like what we would have called an extensile cell. Because the thing is squishy, it can change from contractile to extensile just by being squashed if its shape changes, but the direction of the forces stay the same. So it seems like a rather, if it can just change like that, why can we call it contractile and extensile? So let's do something a little bit different. Let's look at the misalignment angle, that's just what I'm calling it, the angle between the shape axis, all right, which is just the long axis of the cell, and the direction of principal contractile stress. And those are things which you can measure. You can measure the shape axis just by looking at it. And you can measure this stress axis using traction force microscopy. Okay, which I must say I would have been a bit worried about, but our simulations work in exactly the same way, so I'm okay with it.
Is this point similar to the internal
That's what we're assuming. We're assuming that if the cell's pulling like this, it pulls the substrate like that. I'm not an expert on that, but yes, you are. Mm-hmm. Mm-hmm. Okay, well, I'm assuming these things are pneumatic. Yeah. And it's an assumption, but it's an assumption which I can reproduce what's happening absolutely beautifully with pneumatic simulations. But I'd worry about it if I couldn't do that. But that's a big assumption, you're right. Yeah. Yeah. I'm assuming that it's a dipolar stress, right? And I'm looking at the direction it's pulling in along. Essentially, right. Essentially, if you looked at the forces on the cell, it's an assumption that those are dipolar forces, and then I'm looking which direction it's pulling inwards. Mm-hmm. Mm-hmm. Well, mm-hmm. Yeah. Okay. Well, I'll show you the results and then you can complain about them. All right. All right. So this is the picture. This is a picture of what you get. What I'm plotting here is this angle, the angle between this contractile stress axis and the shape axis, the misalignment angle. If that angle is between 0 and 45 degrees, right, it's more or less a contractile cell. If it was perfectly 0, it would be perfectly contractile. If that angle is between 45 and 90 degrees, this thing is behaving in an extensile-like way, okay? It would be like an extensile-like cell. But there's a whole range of these angles. And what you find is that it's mostly contractile-ish. Mostly the angle is between 0 and 45 degrees, but you can get a larger angle in these patches here. And what happens as a function of time is that these patches evolve with time. Okay? This is strange because we had assumed that cells were either extensile or contractile. What it's saying is that this misalignment angle can take any value, more or less stays, 0 is the most likely thing, but then it can be changed to different values. Yeah. Great observation. This is why I first started looking at this data, because I thought, why on earth are they on those angles? And they are. The topological defects sit on these boundaries, and I'm afraid the answer is I don't know why. Okay, we end up thinking about something a little bit different, but that was still an outstanding question. Yeah. Okay, this is a movie of the same thing. Again, experimental data taken, I think, every 15 minutes. And you can see that the extensile patches are evolving with time. And the amount of things can change from extensile to contractile and back again, i.e. the misalignment angle can swing from 45 to less than 45. And if I plot the actual misalignment angle as a probability distribution, okay, you can see that it has it can vary all the way from purely contractile to purely extensile. Things tend to be contractile, but you can have extensile once again. And we did this for 11 different samples, all right? And this was the fraction of extensile and the fraction of contractile. And this sort of shows that if you do a lot of experiments, you get the same story. So how might we model that? Okay. What have I got to do with my active pneumatic equations to put this extra physics in? How would you model it? What extra things would you put in here, right? These are the equations we had yesterday. These are the bog standard active pneumatic equations. What would you do with them to put in this extra thing? Yeah? That's one of the things, yes. You need them to relax back towards each other because things look like they relax back to be contractile. Yeah, that's sort of slide 3, yes. What else? How would we know the different, how would we cope with the fact we've got one direction for stress and one direction for shape? Yeah, ideas? Thoughts? I mean, we've got 2 pneumatic axes here, right, really? One for the shape pneumatic axis and one for the stress pneumatic axis. And so instead of just having one Q tensor, we need 2 Q tensors. We need to really double up these equations so that you have one equation for the stress and one equation for the shape. Yep. And this thing here, the active thing, is just due to the stress. The shape is not got any active, you don't have any active stresses from just the shape of these things, but obviously the stress fibers are what's giving you the contractile stress. And then we need to couple the two cues. And one of the ways they're coupled are just by the flow fields. The stress flow field acts on both the shape and the stress, right? Because if I have a flow field, it's going to change stress fibers, and it's also going to change the shape of these things. And then you have exactly what that lady over there said, a term that puts them back towards each other. So the flow field acts on them in different ways, and then they relax back towards each other. Yeah?
If I think about this classic,
Mm-hmm. Certainly that happens if you have something which can't change its shape, but these things can change their shape, and they can change it in a different way to the stress. So what's happening probably in the biology, we don't really understand the biology, is that the flows are changing the shape, yeah? And you can imagine it doing that quite quickly. If you have a flow, it's easy to unsquish a cell, but it's much harder for flow to change the stress fibers. And so those are going to change on a different time scale. So I don't think that for this system, that is the case, that they have to be connected with each other. Phew. Mm. Yeah, actually, that's interesting because my natural reaction is that it's much easier to change the shape, so that's quicker. But when we measured the correlations, it was actually the stress which changed quicker. Mm. Mm. Okay, okay. Yeah, no, I mean, the way round you said was the way we actually found when we actually measured things. But I was surprised that way round, yeah. There's no reason they should be identical. In long times, yes, but not when they're changing all the time because you've got flow fields mucking them about. Yeah, other questions, yeah? Sorry, can you say it a bit louder? Mm. Yeah. Yeah. Sorry, yes. I went over that a bit. Remember, there's this thing where you relax to the minimum of a free energy. Yeah. That K is the elastic constant in the free energy. And you need the shape and stress to be different in some way because they have to respond differently to the flows in some way. And we do it by putting in a different elastic constant because then we can match the correlation functions. But certainly, we're not sure that's the right way to do it. You could, for example, have a different tumbling parameter, and that would make a difference as well. So that bit there is actually something from the free energy, that one there. I think the answer, so we're saying, do the stress fibers, do they tend to line up in equilibrium? I don't know. I don't know. It's a good question. Yeah. Yep. We're assuming, what we're doing is we're assuming these things are pneumatic, right? Because they do active turbulence. This is another question, and it's one I don't know the answer to. Why on earth are they pneumatic, okay? If you insist on polar forces, fluctuating polar forces would do it for you. I'd always thought, probably wrongly though, it's because the cells are pulling on each other, and that's a pneumatic term. and that dominates over the substrate interaction. So both of those will make them pneumatic. Sure, but we're assuming that the pneumatic term is dominant. So if I'm doing a multiple expansion, right? Let's forget about the polar term and then put in the pneumatic term. And it might be wrong, but they could, yeah. They could indeed. But I don't think it changes well, it doesn't change the story. If we put it in, it would change the numbers, but it would not, first order, change the story. Because when you put friction on an active pneumatic, nothing much changes. Okay? Mm-hmm. Yeah, add one if you like. There's one more parameter which I could do without. But yes, I mean, it's a good idea. Asking how much friction changes things is important. And we've done it with just a simple pneumatic. And the answer is it doesn't change things very much. Yep, okay. Yep.
Microtubule was bending, and then there was a bend instability that sort of goes to the center.
Yeah.
See similar kind of videos with
You see fully, well, depending on which particular MDCKs you look at, you see fully developed active turbulence. Okay, but I don't think anyone's looked at this, looked at how it develops, which you'd need to see the instabilities. We expect them to be bending instabilities. If these things really are active pneumatics, that's what you'd expect. Yeah. Okay. So we ran these simulations. And pretty much whatever parameters we put in that are reasonable, this is what we get. These are the experiments. Remember, what I'm plotting here is this misalignment angle. These are the simulations. And these are what happens evolving in time. So that made me a little bit happier about some of the assumptions that went into the model and the experiments. Okay, we really are seeing pretty much the same thing. We're also seeing topological defects which tend to sit on the boundaries. Yeah, okay, so the lady in green, yeah. We're applying, sorry, what's my plotting here? It's the misalignment angle. It's the angle between the stress and the shape. Sorry, can you shout a bit? Didn't. So the black lines, what are we plotting? Those are the shape, I think. Yeah, sorry. Yeah, yeah.
So in the experiment data, it's like I can see both have defects. They're at the boundaries and they're pointing, they're in from contractile to extensile or the other way. In the simulations, I only ever see them pointing from extensile.
This is essentially the screenshot. You know, this one is the same thing moving with time. So we were only looking at one of them. So that would be a nice thing to measure. I think we did measure it, and I think we couldn't see any sort of trends with it. Yeah. Okay, and we counted the number of defects at the interface, and we compared what happens in simulations with what happens in experiments, and you see again something which is really, really close. I don't believe the quantitative match particularly. I mean, you can fiddle the parameters so it works, but you get this the same story pretty much whatever parameters you put in. So I believe the story. I'm not sure about the actual details, the little details like, you know, what are the elastic constants? Should we have different tumbling parameters and so on? And what I'd really like to understand better is the underlying biology which is doing this. I'll show just one slide on that in a minute. Yeah.
scale, which size of the difference, and do you have any idea of what sensing?
It's about 5-ish cells across, so they're small. They're small, yeah. And remember, they're not quite domains. It's really for visualization. I'm making them red and blue. There, this misalignment angle changes continuously across the things. Yes, we measured things like correlation lengths, and they decay on about 5 cell lengths. I've got all the pictures of correlation lengths, and we can get them to match the experiments with the simulations, but to some extent that's choosing the right parameters, which we don't know what they mean anyways. It doesn't mean much. Yeah. That's right. That wouldn't be the right length scale here, because that's the length scale just for one parameter, active turbulence. This stuff. And so we haven't looked we haven't had time to play with all the parameters in the model to see what we can do. I'll show you one more thing and then make a comment, which is that we tried to look and see what was happening in the cells, because if cells are sort of going to this large misalignment angle, you'd expect the stress fibers to be changing to try and catch up with the shape. And what you can see is that for cells which have a very small misalignment angle, you do get fairly decent stress fibers. And then cells with a large misalignment angle, it's sort of hard to see what's going on. But the experiments are a bit iffy. If you plot the magnitude of the stress against the misalignment angle, again, you see the ones where the shape hasn't been turned away from the stress as being happier, and then it seems to get much more messed up, the ones where you have a large misalignment angle. But I'd like to understand better exactly what is going on in the biology here. Then we heard of some results from Benoit Ladou's group. They did similar experiments and they got similar results, which was great because, you might worry about some of these, but totally independently, they got the same thing about this idea of things having a misalignment angle. But what they found, right, this is all new and probably shouldn't be talking about it because partly I don't understand it. They got a similar picture, but it was mostly blue with red bits in. So these things tended to have been misaligned much more in their experiments than in ours. Essentially, the blue and red were switched over. Panic, right? Someone's got a sign wrong somewhere. Right. So we went through this carefully. And in fact, people, I hope, have not got a sign wrong. What happens is that in their experiments, it's easier for the things to flip from blue to red, from red to blue. It's easier for them to misalign in their experiments. So you get more of these misaligned blue regions. And probably the reason for that is that the cells are moving much faster in Benoit Ladou's experiments. Okay, and so it's much easier to push the cells around. And there's an interesting point there, because if it's easy to push them around, you'd think you'd end up at 50-50, okay? And so the fact that you end up with more misaligned cells means that it's easier to go from contractile to extensile than it is going from extensile back to contractile. And if you start looking at flows and how they squish things, I think you can see pictorially that that's the case, but I'm not going to go into that because I'm not so sure about it. So it's a sort of, we learned a lot of new things with that. Where was I? What time is it? Okay, any questions? And then we'll move on to the next thing, yeah?
The stress tensor slide defects.
Oh gosh, we looked at longer cells and there they do, because the defects get stuck with each other. I think the answer is yes. I think so, but I'm not certain. Good question. those were defects of the shape. I've got them. Yeah.
Model, is the scalar magnitude of the active stress constant, or does it vary?
Constant. Constant. And you might well say that, you know, if the misalignment angle is larger, we should have a stress which is lower, which gradually goes back to what it was before. And that is something we thought we might investigate. Okay. Good. Right. Now let's do something completely different. Let's just now move and think about models. Okay. And in particular, I want to just summarize the sort of models we've got for looking at cells on a scale which is on this sort of scale where cells, you don't see what's going on inside them. You just think really about the forces that are acting on the cells. We've got our continuum models up there, right? And we know lots about those. We've done those for ages. Lisa told you a lot about vertex models, which are, I hated them because they don't look like cells, but I'll show you at the end that they're actually so much easier to handle than what I'm going to talk to you about, which is phase field models. And everything we tried to do with a phase field model, when we tried to do it with a vertex model, it was easier and gave the same answers. Okay, so what we haven't heard very much about is phase field models. So the next bit is I'm going to tell you what phase field models are. All right, so phase field models, what you do is you set up a load of cells by defining a field which takes a value +1 inside the cell and 0 outside. So the cell is defined by field, and there's a different field for each cell. So people often call these multi-phase field models. Okay, and then you put on some sort of dynamic move around like this. And the idea is they look a bit more like cells than the vertex model would. Whether they actually behave a bit more like cells than the vertex model would is the jury's still out for this. But it's a nice alternative where the boundaries probably are a bit more realistic. So each cell is described by this phase field phi I, which is 1 inside the cell and 0 outside, and I is my cell label. The equation of motion for my field is just that it moves with the local velocity, and then it relaxes to the minimum of a free energy, right? So that's very like essentially all these models. They relax to the minimum of a free energy. And then you have also forces acting on these systems, passive forces, which are essentially from the free energy, and then active forces, which you bung in how you want to. And the dynamics is overdamped so that the force is proportional to the velocity. Okay? After one step, there's no inertia in the velocity. Force is proportional to velocity. This is a friction. So let's start with the passive forces, which are relaxing to the minimum of a free energy. How do I define a free energy? Well, basically, I define a free energy so that it looks right. All right? We're basing this on physics, but it's a sensible guess. It's no more than that. This thing here is the usual phi to the 4th theory, and that's organized so that inside my cell, the order parameter is 1, and outside it's 0. And then this thing is a sort of surface tension term, which says that at the edges, I have a nice smooth interface at the edge of a cell. So that sets up the shape of my cells. And by putting on this rather nasty term, it just says that this is essentially a constraint on the area. So the area isn't allowed to change much from some sort of preset area. Makes sense, right? Cells don't suddenly get huge or tiny. Well, they do, but not to a first order. And then we have a term which says the cells don't want to overlap too much. All right, don't worry about the exact details. The important thing is the cells don't want to overlap with each other too much, okay? But then you don't want them flying off, so they're single cells. So you also put in an adhesion term between the cells. So that what you end up with is basically a load of cells which are stuck to each other, but not stuck so hard that they can't move relative to each other. So if you just minimize the free energy, what you'd get is essentially a load of bubbles stuck together. You get a load of hexagons, although sometimes it gets stuck, it gets jammed in a state. And the free energy is organized to do that. And maybe you could think of the adhesion as being relevant to what's actually going on in cells, but you have to sort of guess a bit. Yeah. Could you get away with it? Probably not. Probably you'd be okay. Yeah, because the confinement itself would give you the adhesion. It would stop them all flying away. Okay, so then we've got to put on some sort of active force, because these things are obviously active. And the obvious one to do first is to put on a polar force. So these cells have a certain polarization. All right, so then you say, right, for each cell, I just put a force on the cell, and you could choose to spread it out among the cells, or you could put it all on the center of mass, or you can put it all on the boundary. You can do what you like. And how do you choose the polarization? Well, you could choose it randomly according to some just a noise fluctuation. You could choose it to align with the velocity of the cell. Okay. And you'll probably hear this again if you do flocking in the next lecture. You could choose it to align with the long pneumatic axis of the cell, right? These are just choices. And then we'll see, does it give reality? So let's actually do that. Let's actually put on forces like that. You need some sort of alignment time. And so you might choose a sensible one would be this force aligns with whatever you decide to align it to in a sort of time the cell needs to move its own diameter. And what you end up with this in this sort of model, and actually in the vertex model as well, is that depending on parameters, you can get a jammed state. So what I'm plotting here is just the center of mass of each cell, right? And they're not going anywhere here. You can get a liquid state where the centers move relative to each other. And you can get a state where these things organize and flock, but only if the polarization aligns with the velocity. If you have it random, or if you have it lining with the cell shape, right, you don't get flocking. But if it aligns with the velocity, you do get the flocking state. This is very like VCheck physics, VCheck's model physics. Okay, so we've got it jam, that's good. We've got it flocking. Hopefully this is active turbulence, because we know we see this in cells. So we looked for topological defects, no chance. We looked for the right sort of velocity correlations. No, this is a bog standard liquid. We are not seeing active turbulence in these systems. All right, so modeling these cell layers just with having a polarization in there might work sometimes and does work sometimes very well, but it's not the whole story. So then we tried to put on an active force which is proportional to Q. This is a minus zeta Q force, essentially a dipolar force on each of the cells. A dipolar force sort of spread out among the cell. And I'm going to first of all tell you what happens when you just put a dipolar force on each cell, or you can tell me what happens, all right? So I just put a dipolar extensional force on each cell. I mean, we actually sort of spread it out around the boundary a bit, but basically it's a force like that. What's it going to do with the cell, to the cells? Simple question, even at this time in the morning. Extend the cells, good. And so you're going to get extended cells moving around. What are you going to see? Pneumatic ordering, turbulence, because it's dynamic. So you get active turbulence, you get extensile active turbulence with extensile defects. All right, so that was nice, but you know, cells don't behave like this. Cells don't have extensional forces, right? We know that cells have contractile forces on them. So now if I have my cells and I put on a contractile force, what's going to happen? At least what would have happened about 3 years ago before I actually did the last bit I told you about, right? These things are not allowed to squish beyond circular, right? So if I put on a contractile force, it pushes them back to circular, all right? We didn't know when we did this that they could expand in the other direction. And so you don't get active turbulence. Everything just goes back to circular and nothing moves. Okay, yep. You see topological defects? Yes, I think people say that. Yes, I mean, it's not super well defined, but yes, topological defects and also the velocity correlations show that you have strong vorticity. Yeah, the velocity or vorticity correlations show that. Where was I? Okay, so contractile forces on the cell, nothing moves. So that worried us a bit. So we tried to put forces between cells because if you have a cell, right, it's going to pull on its neighbors and it's going to pull on its neighbors in a way which is equal and opposite. So you certainly do get dipolar forces between neighbors. So let me just tell you what happens. If I have contractile forces between cells, i.e., I put a contractile force on all these cells and ask how it affects this one in the middle, right? So a contractile force on this cell pulls it in here and pushes it out here. Remember, that's what contractile meant, in along the axis and out along the sides. So the way it would affect this cell is by pushing it inwards. Similarly, that one will push like that. This one will pull like that. And this one will pull like that. And so what you get is this thing that extends, yep. And contractile forces between cells actually extend these things, and you get active turbulence. What you get is you get these things being extended and then tending to sit together in really nice pneumatic order, and then very gently you see the splay instabilities of active turbulence. Now I'll just show you one more. Sorry, it's getting a bit hard and a bit late now. So I'll just show you the picture of what happens if these cells are extensile. Oh, actually moves. Cells are extensile, in case anyone's seen a picture like this, because just in case. So if you have extensile forces between cells in this model, the cells want to line up perpendicular to each other. And you can't have everything lining up perpendicular because you end up with this thing being, you can't do that for all the cells at once. So what you end up with is lines where the ones next to the line tend to be perpendicular. These things are trying to be perpendicular. The best they can do is form these lines of aligned cells with the ones next to them being perpendicular. So remember that if anyone sees that, we can certainly see it in rod simulations. Yeah, but it's getting a bit complicated now, so I'll leave this. And just make the point that trying to understand what happens in these models and then comparing to reality, we can see whether the models were right. We can see whether interactions between cells are probably important relative to interactions with the substrate. We can see whether we ought to be thinking about extensile or contractile activity. Right, so just to finish, I'm going to go back to the vertex model. All right. And Lisa told you beautifully about shape in the vertex model. And we learned a lot by looking at this system, what was happening if you have shapes, you know, for the various shapes and whether things are jammed if you have certain shapes of the cell. Can we put dynamics on this thing? And in particular, can we put dynamics on it in a way which we can then take it and map it back onto this continuum model? Because if we're going to have these models, right, it would be nice if they all said the same thing. It would be nice if we could understand the difference between them. And so I'm going to talk about two questions, and I'm not going to talk about them very much because they're fairly technical, and it's what we're thinking about at the moment. But I think, first of all, it's nice to show that you can put dynamics on these vertex models. You can put on active dynamics. And secondly, I think it's fun trying to understand how these things might map onto these continuum theories. So let's take this thing here and let's say, okay, if this really is going to look like an active pneumatic, it ought to flow down a channel. First of all, I can put pneumatic interactions on the vertex model. All right. Essentially, on each cell, you have something which pulls it along its long direction. That sentence hides a lot of work, but let's just take it as read that we can put pneumatic active interactions on this, and it does something which looks pretty much like active turbulence, and we can see topological defects. So if it's going to look like a continuum model, what would be a great test of seeing what's going on? All right, well, let's look at this flow in a channel. Cells do that as well, right? Let's take a channel and say, does it flow down a channel? Because we know that a continuum model, we learned this yesterday, right, flows nicely down a channel. So we did that. Here's the vertex model, and here's the channel, and those pretty colored ones show you what's going on. And the answer is that nothing's flowing. It's not working, right? It's not the same as a continuum model. This is bad because we would like it to be the same as a continuum model. Anybody like to guess what we're missing? Took us ages to work it out. So it's fine. Anybody, what do you think is missing in this model, which we would need? And the answer is allowing it to flow. This thing is overdamped. If you push it, immediately that energy gets used up by the substrate. It's very high friction. So what we tried to do is change the model, okay, with a term like this, which is basically a friction between the velocity of the cells. That's almost like a viscosity. So by putting in this, instead of this damping term, we've got something which is much more like a fluid with long-range velocity correlations. Okay, and if we have a fluid with long-range velocity correlations, the one on the bottom, that's the one on the top, which doesn't, this one here, you can see that it flows beautifully down the channel. Okay. The difference between them is here, we have a real fluid which is flowing. Here, the friction with the substrate basically shortens the correlation length enormously, so you can never get the sort of correlations you need to get the active instability set up. But here you do have the possibility of an active instability. Yeah? Microscopically, it basically takes two sets. You're trying to get rid of the energy somehow. You're trying to put in dissipation, right? The way it's always been put in is friction with the surface. Viscosity puts in dissipation by equalizing velocities. Yeah? And if you put in a term like that, which is actually a huge matrix which couples the R dots from every cell, you're trying to equalize velocities. And that's moving momentum around with long correlations. So it looks like a viscosity.
You don't feel like this is just like, you know, forcing model to do the thing that this flow, or like
well, let's look at the correlations, right? Here's the velocity-velocity correlation. Here's what happens if you have friction. Here's what happens if you essentially put in a velocity. So if I'm mapping it onto an active pneumatic, which is what I want to do, onto a continuum, the dissipation term I need is this long-range dissipation, right? It's like a viscosity term. If I want to stop it flowing, I put a huge friction in my active pneumatic model, and I'll get that. So the important thing was trying to put them together. You know, I can now map them because they do the same thing. I can sort of work out the mapping between them. Yeah.
Will it still flow?
No. You need to look at a correlation length, which is of order this. Yeah, of order the size of the system to get it to flow. So you need to fit in the active instability in there. Okay, other questions? It's like, no, it's an active pneumatic instability, which is what's giving you the flow field. Okay. Oh, this one here. Essentially, yes, it's essentially, sorry, the dissipation is essentially a velocity alignment, and it's very similar to a friction. Sorry, not a friction, that's a viscosity. It's a mock-up of a viscosity.
In vertex models, you already have stresses and, you know, sort of E1 transitions, which is the source of dissipation, right?
Mm-hmm.
So where is this one coming from? I'm saying, like,
You mean in terms of what would happen on a microscopic scale? Basically, just if I have any sort of system, right? It is like viscosity. So if this vertex model is representing a fluid, you need ways of moving momentum over long distances, and this is what that does for you.
right, I'm saying, like, there's already a viscosity in the model.
No, there isn't. There's a dissipation, a local dissipation in the model. Oh, I see. Okay, so you mean if you share it? Yeah. Okay. But you will find that if you look at the velocity correlations, they're small. I'm not quite sure. I've never thought about putting shear on it, but I'm surprised that you don't have problems if you shear it, actually sort of seeing the shear going very far away from the walls.
Yes,
Yeah, I mean, Rasko's on this paper. He's the et al. There. Yeah. Yeah. No, I mean, this is putting Rasko's idea in there. Yeah, that's right. Okay, so one more thing. Again, trying to match what's happening in the continuum to what's happening here. Some of you were asking me about this phase ordering thing, right? I talked about phase ordering in the continuum model. It was due to this active anchoring. Can we get phase ordering in a vertex model? This is a pneumatic vertex model, and I've got a mixture of extensile pneumatic and contractile pneumatic. We tried this with the phase field model. After about 2 weeks of simulation, it sort of staggered to phase separate. This is what a vertex model does in minutes. Okay. No free energy separating it. The extensile ones and the contractile ones separate relative to each other. But I think this is a totally different mechanism that's happening in the continuum system. What we think is happening here is that the extensile cells, the blue ones, move rather quickly. The contractile cells are pretty much not self-propelled. The extensile ones push the contractile ones next to each other. And then the contractile ones tend to stick to each other. And they tend to stick to each other because there's a sort of elasticity, because they tend to elongate, just like we saw contractile ones tend to elongate with neighbor interactions in the phase field model. Okay. And so if you try and pull them apart, they get upset because they want to stick to each other and be extended a bit. Okay. So let me get to the end. Can I show you the movie? I haven't gone through the bit about the movie. This is my hare and tortoise story, but it was only on there really just to. It's all right, you can just still see the movie. You don't have to hear the noise. Okay. And there's a Nature paper, which I really wanted to call the hare and the tortoise paper, but my collaborators said it wasn't allowed. So, sorry, Nature physics paper next to the one about Hydra, if anyone wants to see why that movie comes up. Okay, so what next? Those are things I think is interesting at the moment. No doubt you've got your own things which is interesting. But let me finish by just saying thank you very much. I wouldn't do anything without the amazing students and postdocs in my group who explain everything to me and do all the work. And this is some of the recent ones. I hope all of the recent ones, but there's no one going to be upset about this. Thanks very much for listening, and happy to take questions. Okay, any questions? Yeah, one at the back there. Yes, you get vorticity, you can get topological defects, you can definitely get active pneumatic-y like things. There are actually two ways of doing it, right? We did it one way where you end up with +1 defects for reasons which are strange, but doable. Matthias Merkel did it a different way, and I think his way is much more mappable onto the continuum, and that's a really nice paper, I think, to look at. Yeah. Mm-hmm.
In the continuum model, the scale of the active turbulence is given by some parameters.
Yeah. Yeah, root K over zeta, yeah.
Yeah. Is it fair to say that that comes up in the vertex model is just taking in those parameters?
We don't know. There have been a few attempts to map vertex models onto the continuum, I think by Dresden people, for example. But there's not a clean mapping to the way I think about the continuum model, all right? And I think that's an important thing to understand better. We're sort of working on it, but it's not easy. Yeah. Yeah, Jim. Mm-hmm. Yeah, the Ulick group have made progress with that. Yeah. Oh, what's lambda? I don't know actually, because that's a very good question. We don't know. We don't know because this sort of stuff about a wet vertex model is quite new. And it's not obvious what lambda is, right? Because you don't put it in like you do in the equations, but we could presumably measure it by looking how these things move under shear. I don't know, maybe that's gone. So, but it would be a very interesting thing to measure. Don't know. Good question. Good. Okay, well, it's coffee time. Thanks very much for listening. And yeah, happy to